Okay, so this is one problem statement where I do have a Pelton wheel. Okay, I am trying to solve the problem on the Pelton wheel, and I'm going to solve using the velocity triangles here. A double jet Pelton, the problem is something like this. A double jet Pelton wheel is required to generate 7,500 kilowatts when the available head at the base of the nozzle is 400 meters. The jet is deflected through 165 degrees and the relative velocity of the jet is reduced by 15% in passing over the buckets. Determine 1. The diameter of the jet, the total flow, that is the discharge, and the third one is the force exerted by the jets in the tangential direction. Assume the generator efficiency is around 95%, the overall efficiency is around 80%, and the speed ratio is 0.47. So this is the problem statement. So the solution, let's try to solve this. So what is given? So the given is you have a number of jets, that is n is equal to 2, and I have the generator part. Okay, let me call that as P generator, which is 7,500 kilowatts. Okay. Then the head under which your turbine is working is 400 meters, and I have, see, the jet is deflected by this much of angle. What do you mean by it actually? I'll write a sketch and then try to explain. Say for example, this is, suppose this is my blade of your Pelton wheel, something like this. This is how it is. This is how it is, and if I try to put an axis for it, something like, if I try to put an axis along this particular direction, if I try to draw a velocity triangle here, so what will be my inlet velocity triangle? The inlet velocity triangle will be a straight line, where this will be equal to V1 is equal to VW1. Okay, then I will be having U, and then I will be having your VR1. This is what we have. Now what's happening here? See, the jet is getting deflected by 165 degrees. That means the jet will strike in this direction, and somewhere if I try to draw the deflection angle, if I try to draw a deflection, it is getting deflected something like this. This is what the deflection. Okay, that means it is deflected by 165 degrees. That is, this is 165 degrees. If I try to draw the beta, so then this will be my beta 2. Okay, then what is your beta 2? Based on the deflection angle, I can write your beta 2 is equal to 180 minus, if I call my deflection angle as theta, it is 180 minus theta, that is 180 minus 165. So it is 15 degrees. So my beta angle is 15 degrees. That's the meaning of it. The jet is deflected through 165 degrees. So in some of the Pelton problems, either they can use the deflection angle or directly they can use the exit beta 2 angles. Actually, they can use. So now using this, I can draw the velocity triangle. Let me complete the velocity triangle. So if I try to draw the velocity triangle, it will be something like this. Okay. So this will be my VR2, and this will be my V2, and I have, this will be my VF2, and this is my VW2, so that this is alpha 2, and this will be my U2. Okay, U2 is equal to U1, whatever it may be here. I don't have U1, U2 and all, both will be same. This will be, let me call it as U, and this will be in this direction. Okay, so this is what I have. Okay, this is what I have. So this particular thing, sorry, this is U. This is U, because the U is starting from here. This is my U. is my U. So this is my Q, because this is between your V2 and VR2. And this will be my beta 2, which is equal to this angle. So I'm able to write the corresponding, because this particular velocity triangle I drew it to show the deflection angle. Now let us write the other data what is given. So they are given there is a reduction of 15% in, see, the velocity of the jet is reduced by 15%. What is velocity of the jet? It is relative velocity. So that means your VR2 is 15% reduction, that is 1 minus 0.15 into VR1, that is 0.85 VR1. That's the meaning of it. There is a 15% reduction, means it is 0.85 times. Then they have given the generator efficiency, which is 90% or 95%, okay, 0.95, and overall efficiency is 80%, and they are given the speed ratio phi is equal to 0.47. This is what they are given. What we are supposed to find? Okay, the first thing you have to find is the diameter of the jet. The second one is your discharge. The third one is the force exerted by the jets in the tangential direction. Let me call that as Ft or F tang or whatever it may be. Now, see, this turbine, it has, you see, if you try to look into how the construction is, where is my generator? Usually how it is actually, if suppose this is my turbine, so the steam gets water gets expands like this, and this is my turbine. Okay, this is my turbine, and to this turbine, I am going to have your generator. Okay, this generator is used to produce the electricity. So this is your some power or whatever. This is the shaft power, and what is given is the generator power. So generator efficiency means what actually? See, your generator efficiency means it is the power available at the generator to the power available at the shaft, this power. If I can call this as shaft power. If I take the ratio of it, I'll be getting generator efficiency. So then what is your shaft power? Your shaft power is equal to your generator power divided by your generator efficiency, that is 7,500 divided by 0.95, that is 95%. I am getting it is around 7895, 94.75 or 7895 kilowatts. So your shaft power is more, 7895 kilowatts, and your generator power is around 7,500 kilowatts. This is how you can find your shaft power. Once you find your shaft power, then I can go and find your discharge, all the things one by one I can find it. Okay. Now let us find the particular discharge. So what is it actually? We know that the overall efficiency. So we know that the overall efficiency is given by your shaft power to your energy available at the inlet of the fluid, that is your omega Q into H. So they have given the overall efficiency as 80%, that is 0.8. Shaft power just now we calculated, it is 7894.75, round it off to 7895 into 10 to the power of 3. So it is in watts divided by your omega is 9810, that is 1000 into 9.81 into Q into head under which this turbine is working is 400 meters. If I substitute everything, I am getting my Q as 2.52 meter cube per second. Okay, then I am getting my Q as 2.52 meter cube per second. This is the first thing. Now to find the diameter of the jet, what I am going to use? So we know that discharge through a Pelton wheel, that is Q is equal to number of jets into area of the jet into your velocity of the jet. The velocity of the jet. But I don't know the velocity of the, what is it actually? Velocity of the jet, I can find it based on your root 2gh if it is theoretical. Suppose if it is, if I assume CV is equal to 0.98 or something. So here, if I assume CV is equal to any number between 0.98 to, maybe you can take it as 1 also, doesn't matter. So here they are not given in the problem, you can take anything. So if I take CV is equal to 1, so because already we have taken 0.98, let's try with CV is equal to 1. Then your CV is equal to, sorry, your velocity, sorry, not CV, your velocity V1 is equal to just simply root 2gh. That is 2 into 9.81 into 400. If I take a root of it, I am getting this as 88.6 meters per second, which is also equal to VW1. If I take 0.98, this number will be less than 88.6. Okay, so you are getting 88.6. So this will be, so if I take it as 0.98 as CV, this would have been 86.8. So that's it. It all depends on what value you are taking. If I take CV is equal to 0.95, this number will come down. Okay. Now, what is your Q value? Q value is 2.52 just now. So substituting this values, all those things in my discharge formula. So if I substitute, Q is 2.52. So here the number of jets is 2. Pi D is what I am supposed to find into V1, just now we found it as 88.6. So if I substitute everything, I am getting my D as 0.134 meters or 134 mm. Suppose this value of jet is less, in that case the diameters are going to change. Okay. Now the second thing is I need to find the what is called as your tangential force, all those things. To do that, I will be see what is your tangential force. Your tangential force is nothing but your VW1 minus VW2. I need to look at the tangential force VW1 minus VW2 into its corresponding whatever you have, that a mass or mass flow rate, whatever the discharge or whatever. If you look into it, you will be getting your tangential force. So to find that VW1 and VW2, I'll be going to your velocity triangles. So let's try to find each one by one. To do that, the first thing I'll be finding is your U. Okay. So we know the speed ratio is given by U phi is equal to U by V1, or I can write U is equal to phi into V1. So phi is actually how much? It is given as 0.47 in the problem statement. 0.47 into 88.6. I am going to get my U is equal to 41.64 meters per second. So this is the value of your peripheral velocity or blade velocity. Now let us go back to inlet velocity triangle. So this is the inlet velocity triangle. See, from the inlet velocity triangle, what is VR1? VR1 is equal to V1 minus U. Okay. What is your VR2? VR2 is given in the numerical statement as it is 15% reduction. So VR2 is equal to 0.85 times VR1. So I need to find VR1 first, then I can find VR2. Okay. Then now if I try to come to exit velocity triangle, what is sine beta 2? If I take sine beta 2, which is equal to your opposite side, that is VF2 divided by VR2. So sine beta 2 is equal to opposite side, so your opposite side by your hypotenuse, that is VR2. So from that, I'll be calculating your VF2. Now similarly, what is your cos beta 2? Cos beta 2 is equal to your adjacent, that is U minus VW2, this one, this value. Okay, divided by VR2. From that, I'll be able to get my VW2. So VW1 is equal to V1, VW2 is equal to VW2. I'm trying to calculate. Take the difference of it, multiply by your corresponding mass flow rate. I'll be getting your tangential force. That's what I'm trying to do it. So one by whatever I explain, that I'm going to do in the next few steps. The first thing is, let us try to take the inlet velocity triangle. So from the inlet velocity triangle, from the inlet velocity triangle. So VR1 is equal to V1 minus U. So V1 is 88.6 minus U1, just now we calculate, is 41.64. I am getting my VR1 as 46.96 meters per second. Now in the problem statement they are given VR2 is equal to 0.85 times VR1. So this is 0.85 into VR1 is 46.96. I am getting my VR2 as 39.92 meters per second. So now consider the exit velocity triangle. So consider the outlet or consider the outlet velocity triangle. Sin beta 2 is equal to Vf2 divided by Vr2. So Vf2 you are supposed to find. Beta is 2 is how much? 15. So sin 15 is equal to, so Vf2 as it is, and Vr2 just now we found it as 39.92. Therefore my Vf2 is equal to 39.92 into sin 15. If I multiply, I am getting 10.33 meters per second. Now similarly, cos beta 2 is how much? Cos beta 2 is equal to adjacent, that is u minus Vw2 divided by your Vr2. Okay, so that is cos 15 is equal to u is 41.64 and Vw2 I don't know, Vw2 I am supposed to find, divided by Vr2 is 39.92. So Vw2 is equal to 39.92 into cos 15. So if I Vw2, if I take to the left hand side, it will be 41.64 minus of 39.92 into cos 15. If I do that, I am getting around 3.08 or roughly 3 meters per second. I got my Vw2. Then what is the tangential force? So therefore, the tangential force Ft is equal to your mass flow rate into Vw1 minus Vw2. So what is your mass flow rate? Mass flow rate is equal to density into discharge. So what is your density of water? Is 1000. What is your discharge? Is 2.52 meter cube per second. Substitute all those things. That's what I am trying to do. So this will be 1000 into 2.52 into Vw1 is, which is equal to V1. See, Vw1 is equal to V1, that is 88.6 minus Vw2, just now we found it is 3.08. If I substitute, I am getting my Ft as roughly around 215 kilonewton. So this is the force, tangential force exerted by your turbine. I have found all the things. If you go back and check what are the things which you are supposed to find, the diameter of jet we found, discharge we found, and tangential force. All the three things we are able to find it. Is that clear? So this I would say you may get this kind of problems. Maybe one of the data may be given in the problem, or one of the data you may have to find it. So here from the deflection angle I have to find a beta 2. Maybe in some other problems they won't give the deflection angle, they may give directly the beta, or they may give one of the velocity of the flow and you have supposed to find other parameters. So the methodology wise, actually you have to use your trigonometric principles. What is given, and you have to take it and you have to solve the unknown things. Okay. Now let us try to take one problem on Francis turbine. Its problem statement is something like this. A Francis turbine is to be designed for a flow rate of 2 meter cube per second, available at a project site at a net head of 10 meters of water. And one thing you have to remember here is your Francis turbine, Kaplan turbine and all, they work under lower head. If you look at the Pelton wheel, they work under very high heads, maybe 300 meters, 350 meters and all. And your Francis turbine, they'll be working at 10 meters, 20 meters, 30 meters like that. So they're all low head turbines or medium head turbines. Okay. The extended overall efficiency of is around 80%. The speed coefficient and flow coefficient can be assumed as, or it's given as around 0.8 and 0.6, so depending upon some design data. The hydraulic losses in the turbine are 15% of the available energy. What do you mean by it? The hydraulic efficiency is 1 minus 0.15, that is 85%. That's the meaning of it. Okay. Design the turbine rotor with salient dimensions and angles to run at 300 RPM. Okay. The water leaves the rotor without any whirl component. So you have to find each and everything. Then you have to find alpha, you have to find beta, beta 1, beta 2, all the things you have to find it. U1, U2, everything you have to find. That's why it is called as a design. Okay. So it's a design problem. So let's try to find a solution for it. So let's write the what is given. So given is Q is equal to 2 meter cube per second, and the head under which it is working is 10 meters. The overall efficiency is 0.8, 80%, and the speed ratio, that is, it is 0.8, and the flow ratio or flow coefficient, that is psi, which is 0.6, and the hydraulic efficiency, which is 15% of the losses meant, it is 0.85 or 85%, and they have given the speed under which the turbine is working as 300 RPM. And they are telling that the water leaves the rotor without any whirl component. That is, it is leaving radially. That is, my alpha 2 is equal to 90 degrees and VW2 is equal to 0. This is what they are asking. And what they are asking? They are asking is to design everything. So design means what are the things which you are supposed to find? The first thing, you have to find both U1 and U2, which is being a radial turbine, U1 and U2. Fine, that's one thing. And you are supposed to find the flow velocities, VF. And you are supposed to find the diameters, D1 and D2. And you are supposed to find the blade angles, beta 1 and beta 2, and the power developed. So all the things which you have to find when you are trying to design it. So let's go one by one, step by step. We'll try to derive it. Okay, try to solve this problem. Okay, we know that speed ratio, the speed ratio phi is given by U by V1, or it is U is equal to phi into your root 2gh. This is the formula what we have. But in case of a radial flow machines or your this thing, this will be U1 instead of an average U. So that means I know phi is given as 0.8. I know the value of h is equal to 10 meters. Let's substitute everything. So U1 is equal to 0.8 into 2 into 9.8 into 10. I am getting my U1 as, so if I try to calculate, is around 11.2 meters per second. 11.2 meters per second. Now, what is your psi? That is flow coefficient. It is actually, it's the ratio of, see, the flow coefficient. The flow coefficient psi is equal to Vf divided by V1. Okay, Vf divided by V1, or I can write Vf is equal to your psi into root 2gh. So psi is given in the problem statement as 0.6. So I can find that is 0.6 into 2 into 9.81 into h is around 10 meters. So I am getting my Vf as 8.4 meters per second. So therefore, this is my Vf, this thing. Now I need to find the power. I can find the power. So they have given the overall efficiency. The third one is the overall efficiency is given as the overall efficiency is equal to P divided by omega QH, or P is equal to overall efficiency into omega into QH. I would have got this number. So overall efficiency they are given it as 0.8. So omega is 9810. So Q is 2. They are given 2 meter cube per second, and head is 10. So I have got my power, that is a shaft power, as 157 kilowatts. Okay. Now I need to go and find the one by one. So D1, U1, one by one I need to find it. So next thing, it's a complete design actually. The next thing, let us find the specific speed. Okay. Let us find the specific speed of the turbine. Specific speed of the turbine. So it is given by NST is equal to N root P by H to the power of 5 by 4. Okay, speed they given it as 300, and P I need to substitute in kilowatts directly, 157 divided by head is 10. So 10 to the power of 5 by 4, if I do that, I should get a bigger number, because this being a reaction turbine, this should be a higher number. For a Pelton turbine, this will be a lower number because it is working under a higher head. So NST specific speed is around 211.4 RPM. Now what is my U1? U1 just now we found. So from that U1 I can find the D1. Okay. The peripheral speed. So that is blade speed. Blade speeds. U1 is equal to pi D1 N by 60, or D1 is equal to 60 into U1 by pi into N, or D1 is equal to 60 into, what is my U1? It is 11.2 divided by pi into speed is 300 RPM. I am getting my D1 as 0.7 meters. Okay. Now I hope you remember that your speed ratio or diameter ratio, I can assume something. So here I have to do something because it's a design problem. If I assume D2 by D1 as something around 0.6. Okay, your or D1 by D1 by 2 as something around 0.6 if I assume. So D1 is something around 0.7 meters. So your D2 will be, so your 0.7 divided by, so D1 is my outer diameter, D2 is inner diameter. So if I go by that logic, D2 by D1 is 0.6 to 0.7, I can assume anything. So D2 by D1, roughly any number between 0.6 to 0.7. Hope you remember in the design thing I was discussing this particular thing. So if I go with 0.6 itself, then what will happen to your D2? So D2 is equal to 0.6 times your D1. So this will be 0.6 into 0.7. So this will be 0.42, that is some 6 of 42. So it is 0.42 meters. So inner diameter is 0.42 and outer diameter is 0.7 meters. So what is my V1? If I want to find V1, see V1 is equal to your, see this is my V1. V1 is equal to root 2GH. So V1, can find that V1. So V1 is equal to, it is root 2gh. V1 is equal to root 2h, assuming CV is equal to 1. Okay, that is 2 into 9.81 into 10. So I'm getting around 14 meters per second. So these are the parameters what we have. Okay. Now if you want to draw the velocity triangles, because I need to find VW1, alpha, all those things. Okay. If I want to do that, let us try to draw the velocity triangles. So if I want to draw the velocity triangle, let's try to draw the blade. So the blades are something like this. So this is my blade which is curved, and this will be rotating in anti-clockwise, this being a turbine. If I try to draw the velocity triangle at the inlet, so this is my your VR1. Let me call this as VR1, and I have my V1 is something like this. This is my V1. Let me complete my triangle. This will be my U1. This will be my U1. Okay. So this is my alpha 1. This is my beta 1. I can complete the triangle. Here I can complete the triangle. So this will be my VF1, and this will be my VW1. I got my inlet velocity triangles. If you call this as some x, okay, x is equal to u minus VW1. Okay, and also here VF1 is equal to PF2 until unless there is a great reduction in the flow. Now at the exit they are given alpha 2 is, that is, it's radially exiting. There is no whirl component at the exit, it's given the problem statement. So at the exit what will have? I'll be having a triangle something like this. It is going like this. So this is my VR2, and I'll be having a simple right angle triangle at the exit. It's a simple right angle triangle. This is my alpha 2, and this is my beta 2. This is my VW2, which is equal to VF2. Sorry, V2 is equal to VF2, and VW2 is equal to 0, and this will be my U2. So all the things I have put in your velocity triangle, all the ingredients, that is VF, VW1, everything is there. So now let us try to find one by one from the given what it is. So they are given hydraulic efficiency. What is your hydraulic efficiency? See, hydraulic efficiency they are given. I can try to find the given VW1 or VW2, whatever is this particular, I can find it. Say hydraulic efficiency is given by the hydraulic efficiency, that is hydraulic efficiency is given by the sixth one. Hydraulic efficiency is given by your Euler head. What is Euler head here at actually? It is VW1 into U1 minus VW2 into U2 divided by G divided by your head under which your turbine is working. So this is your Euler head. This ratio is called as your hydraulic efficiency. But in this problem statement, my VW2 is equal to 0. So in that case, what will happen to your hydraulic efficiency? Your hydraulic efficiency is equal to, it's only VW1 into U1 divided by G into H. So this is the simplified formula what we have. So they are given hydraulic efficiency as 85%. That is 15% of the hydraulic losses means it's 0.85. If I substitute 0.85 is equal to VW1 into U1, just now we found it, it is 11.2 divided by G is 9.81 and H gives the problem statement as 10. I can calculate my VW1 is equal to 7.45 meters per second. Okay, this is your VW1. Now, what we will do is actually, this is your VW1. So I need to find your other things, VW2, VW3, sorry, VW2 and your, sorry, alphas and betas we need to find. Alphas and betas we need to find. So to find that, let's try to consider the inlet triangle. Let's come back to this. If I try to look at the inlet velocity triangle, one in the blue color, what is your tan alpha 1? Tan alpha 1 is equal to opposite, that is VF1 divided by your VW1. Okay. VW1 just now we found it at 7.45. So VF1 is 8.4. So we found it that also. Take the ratio of it. Take tan inverse of it, you will get your alpha 1. Then what about your beta 1? If I want to find it, tan beta 1 is equal to once again VF1 divided by your x. That is U minus VW1. So I'll be able to calculate my alpha 1. I'll be able to calculate my beta 1. Okay. Now coming to the exit velocity triangles, I know my alpha 2 is 90, but I need to find beta 2. So to find that, if I take tan beta 2 is equal to opposite side, that is VF2 or V2, which is equal to VF1 divided by your U2. Now U2 will be actually what it is. My D2 is equal to 0.6 times of your D1. Your U2, see from there, it's also implying that your U2 by U1 is also between 0.6 to 0.7. So whatever the ratio I assume, 0.6 means your U2 is also equal to 0.6 times of your U1. So from that I can calculate my U2 and try to calculate your beta 2. So that completes your design. That completes your design. That is alpha, beta and everything I am trying to find. Alpha 1, beta 1, everything I am trying to find. So let's go on. Whatever I discussed, so that let's try to calculate and put in the numbers. From the inlet velocity triangle, okay, tan alpha 1 is equal to VF1 divided by VW1. Okay, so tan alpha 1 is equal to VF1 is 8.4. If you go back and see everything we have calculated, VF1 is how much? 8.4, which is also equal to, it is also equal to VF1, VF2 both are same. And VW1 just now we have found it, it's around 7.45. So I am going to substitute that 8.4 divided by 7.45. So alpha 1 is equal to tan inverse of 8.4 divided by 7.45. If I do, I am getting my alpha 1 as 48.4 degrees. Okay. Similarly, what is your tan beta 1 from the inlet velocity triangle? Tan beta 1 is equal to VF1 divided by your U minus VW, that is U1 minus VW1. Okay, tan beta 1 or beta 1 is equal to tan inverse of, what is your VF1? It is 8.4. What is your U1? It is 11.2 minus 7.45 is your VW1. I am going to get my beta 1 as tan inverse of it. It is 65.86 degrees. So similarly, now this is from the inlet velocity triangle. From the outlet velocity triangle, tan beta 2 is equal to your opposite side, that is VF2 divided by your adjacent, that is U2. But I don't know my U2. So U2 is equal to, I will go with the same assumption, 0.6 times your U1. U2 is equal to 0.6 into 11.2. So your U2 is equal to 6.72 meters per second. And then substitute over here. So beta 2 is equal to tan inverse of VF2 divided by U2. I can substitute it. So beta 2 is equal to tan inverse of What is your VF2, which is 8.4 divided by U2 is 6.72. I am going to get my beta 2 is equal to 51 degrees. So all the values, so they are told you to design. So we have designed completely what is given there. Everything we have designed. So alpha 1, beta 1 and beta 2, everything we have done. Is that fine? So like this, you can solve any kind of problems. You can solve any kind of the problems. So it is 220. Okay. Let's try to solve few more problems. Yeah, on draft 2, we'll try to solve one problem and we'll try to wind up. So it'll take some water, 2 minutes time. So if you have any doubts, you can unmute and you can speak. You have any doubts? Anyone, whoever it is, no problem. You can unmute and speak. I think we'll wind up with this particular problem. This problem we'll do and we'll try to do. And there is one Kaplan problem. I'll try to solve that and try to upload it. So with that, I think we'll try to wind up this particular thing. If there are any requirement comes, we'll try to do sometime, maybe sometime after your test. No, we'll try to solve it. Okay, fine. So this is your problem on the numerical on draft tube. A head available at the inlet to a Francis turbine is 28 meters. The output of the turbine is 1000 kilowatts. Okay, then at the overall efficiency of 0.88 when there is no draft tube attached to the exit of the turbine. The level of the turbine is 2.5 meters above the tail race. The flow coefficient of the turbine is 0.3. Assess the effect of installing a straight cylindrical draft tube and a draft tube with the half cone angle of 5 degrees at the exit of the turbine. What is it actually? I am going to have a cylindrical draft tube as case A, and case B I am going to have it as a conical draft tube. The efficiency of the draft tube may be taken as 95% in either case. Both the cases, this is what they are given. So let's try to write the data solution. So what is given? So they are given the Francis turbine with a available head as 28 meters. The power is 1000 kilowatts, and they are given the overall efficiency as 88% or 0.88. Okay, and they are given the flow coefficient, that is psi is equal to 0.3, and they are given the we call that as Z2, that is the height of that particular, the level of the turbine is 2.5 meters above the tail race, that is 2.5 meters above your tail race where is your turbine is located. They call that as Z2. When I draw the sketch, you will try to understand that. Now we need to analyze this particular thing for both cases. First case, let's take for the first case, cylindrical draft tube. Cylindrical draft tube. What is the cylindrical draft tube means? The draft tube is almost like a pipe. If I try to have an axis like this, if I have a axis like this, because these draft tubes are installed vertically in case of this particular, in case of a thing, that means if suppose this is my D2, suppose this is my D2 and this is almost, It is running vertically like this. It's almost a completely a straight line. It's almost completely a straight line like this. It's a cylindrical draft tube like this. It's a cylindrical draft tube. If I call this as D2 and this as D3, this is section 2, that is exit of the turbine, 3 exit of the draft tube. See, I go by the same convention. 1 is the inlet to the turbine, 2 as the exit of the turbine, and 2 is the inlet to the draft tube, and 3 is the exit of your draft tube. Okay. Now, suppose this is my datum. Say, for example, this is my datum. This is my datum. So, what they are given is, this is my Z2, which is 2.5 meters. So, what will be a Z3? Z3 is equal to 0. Z3 is equal to 0. So, this is the simple construction of a cylindrical draft tube. Let's now try to analyze for this particular condition. So, before analyzing, let's try to find the data, all those things are done. So, they are given overall efficiency. The overall efficiency is nothing but your shaft power divided by omega QH. So, from this I need to find the discharge. So, Q is equal to, okay, it is power divided by the overall efficiency into omega into H. Let us substitute everything. So, power they are given it as 1000 kilowatts. It is 1000 into 10 to the power of 3 divided by, it is overall efficiency is 0.88 and omega is 9810 and the head they are given it as 28 meters. If I substitute everything, I am getting my Q as 4.14 meter cube per second. Okay. Now, they are given the flow coefficient, which is psi, which is equal to your Vf divided by V1. So, Vf divided by V1, okay, or Vf is equal to psi into your V1 is nothing but root 2gh. So, if I substitute, Vf is equal to point C is the psi divided multiplied by 2 into 9.81 into H is 28. So, my Vf is equal to 7.1 meters per second. Okay. So, now this is my Vf, this particular thing. Now, what is my discharge? See, discharge is given by, see, discharge Q is equal to your pi into d2 square by 4 into your Vf. Okay, what is your discharge? It is 4.14 meter cube per second into pi into d2 square by 4 into Vf is 7.1. I can find my diameter, which is roughly around 0.865 meters, which is also equal to your D3, because this is a cylindrical draft tube. So, the diameters remain the same. So, the diameter remains the same. Now, let us try to apply the Bernoulli's principle between section 2 and section 3. Okay. Now, let us try to apply the Bernoulli's equation. Applying the Bernoulli's equation between section 2 and section 3. Hope you remember that I have done a derivation. So, from the derivation I am going to use the final equation, that is P2 by omega is equal to PA by omega minus H minus 1 minus K into V2 square minus V3 square by 2G. This is the formula what I used in this particular thing, where this is your head. See, H is nothing but it is the head, and head means It is the head above your tail race where your turbine is locating. That is here, it's around 2.5 meters. And what is your 1 minus K? This is your what is called as, we call it as draft tube efficiency. Draft tube efficiency. So this is your Z2 or what we have in this particular problem. Now one advantage here, see, one disadvantage what we have is if I am trying to use a cylindrical draft tube, what is your discharge? See, Q is equal to A2 into V2 is equal to A1 into V1. My D2 is equal to D1. Automatically for this cylindrical condition, you have where V2 is equal to V3. B2 is equal to V3. So this term automatically becomes 0. What I am left with actually, in that case I am left with the formula becomes P2 by omega is equal to PA by omega minus H. That's all. So what is your PA by omega? See, PA by omega means your atmospheric pressure divided by 9810. If you refer any of the standard fluid mechanics textbook, that number is, it is the pressure at the sea. What is P2 by omega? See, this is the pressure at the exit of the turbine, P2 by omega, or pressure head, we call it as pressure head. Okay, pressure head at the exit of the turbine, or the runner, it's also called as a runner. Now, if I try to substitute it, that is P2 by omega is equal to, how much is PA by omega? It is 10.3 minus 2.5. Or try to find only in terms of pressure. So this I can write it as P2 is equal to 10.3 minus 2.5 into 9810. So this I am going to get in terms of meters. This I am getting in terms of your pressure. So this will be 7.8 meters. Okay. This is around 76.52 kilopascals. 76.52 kilopascals. Either you can substitute this value or get this value in terms of pressure head or in terms of pressure. So both are, so this is what we are trying to, so this is the pressure at the exit of the runner. So now let us try to analyze your conical draft tube and see what is the pressure. What is the pressure at that particular thing? If that pressure at the exit of your turbine is much less compared to what I am getting. Suppose if I am getting 76.52 or 7.8 meters. Suppose in case of your conical draft tube, if this number is less than 7.8 meters, then I am going to prefer a conical draft tube compared to this one, because I am able to recover some amount of pressure, recover some amount of energy. I am going to save that particular energy is recovered and converted to some kind of an response. So that's what we will try to look into that. Then we will try to comment on it. Now let's try to draw for the conical draft. Now let us try to go for the conical draft. Second case is the conical draft tube. Conical draft tube. So now let us try to draw this actually. So this is my cone. This is the axis, the center axis, and at the top I have the big smaller diameter, and at the exit I have the slightly a bigger diameter, and trying to give a little bit of, this is around, alpha is around 5 degrees. What is it actually? See, it's also once again D2. See, this is also equal to D2. Now if I try to draw the same thing what I had for the conical draft tube to your cylindrical draft tube, the difference is only this much. That means I have an alpha, this alpha is equal to 5 degrees, that's all. So alpha is equal to 5 degrees, because although this is my D3. So this is your section 3.3. This is section 2.2. Okay. So now if I call this as some x and this also some x. What is your D3? This is your D3. D3 is equal to D2 plus 2 times your x for alpha is equal to 5 degrees. So that's how I can find the D3. What is the cone angle? It is alpha 5 degrees and I can find the D3. So D2 is equal to how much? And D2 is actually how much we have and D3 is equal to how much we have. So D2 is equal to, so it's around 0.865 meters. Okay, 0.865 plus 2 times your 2.5 times your whatever is that particular thing they are given. So this height is once again, this is your Z2. Okay, this is your Z2 and this is your datum, your Z3 is equal to 0. Okay, so D2 already we have found is equal to 0.865 meters. Now what is your alpha? So if you look into this particular right angle triangle, tan, so this is your 90 degrees. Tan alpha is equal to your x divided by 2.5 or your x is equal to 2.5 tan alpha is 5 degrees. Okay. Now what is your D3? Your D3 is equal to your D2 plus 2 times your x. Okay, 2 times your x. Or I can write D2 plus 2 into x is actually 2.5 times tan 5 degrees. I substitute that is 0.865 plus 2 into 2.5 into tan 5 degrees. Tan 5 degrees plus 0.865. If I add, I am getting my D3 as 1.302 meters. Or let me take 1.3 itself. 1.3 meters. This is my D3. Now, what is your discharge? Okay, discharge is given by Q is equal to A2 into your corresponding V2 or whatever is there. So V2 is nothing but your VF, whatever is there. So if you go and look into this VF is also equal to your V2 because this is at the exit of this particular thing. Whatever that particular thing is also equal to velocity of the flow. You call that as V2 is equal to A3 into V3. Then what is your this particular? So then I know my discharge. So I can find my V3. So V3 is equal to Q divided by your D3 that is A3 that is 5 into your D3 square by 4. If I substitute Q is 4.14. If I take the denominator to the numerator, this is 4 into pi into your D3 is 1.3 square. I am getting my V3 as 3.1 meters per second. In the previous case, V2 was equal to V3. But here if you look at it, V3 is getting reduced. So if I take V2 as 7.1 meters per second, we calculated. V2 as 7.1 meters per second. Hope we remember, we calculated it as 7.1 meters per second from the VF. So now that value is getting reduced to 3.1 meters per second. Now let us try to apply the Bernoulli's equation for these conditions. So applying the Bernoulli's equation between section 2 and section 3. If I do that, so I'm going to use the same formula. It is P2 by W is equal to PA by omega minus H minus 1 minus K into V2 square minus V3 square by 2 into G. Here V2 and V2 they are different. Let's substitute everything. So this is 10.3 meters minus 2.5 minus C. What is the minus K? It is hydraulic efficiency, which is 95%. 0.95 into your V2 is 7.1 square minus 3.1 square divided by 2 into 9.81. If I substitute everything, I am getting my P2 by W as 5.8 meters, or I can write P2 is equal to your 5.8 into 9.9810. 9810, your pressure is around 56.9 kilopascals. So what we can comment? We can comment something like this. From the first case, see, I was able to see if I have a cylindrical draft tube, how much I was saving? I was saving only around 2.5 meters was saved. That is 2.5 meters of your head is saved. What is it actually? So usually speaking, this pressure should be P2 and this P2 PA by W both should be 10.3. But here in second case, what I am trying to say, 10.53 minus C. If you look at it here, I am able to say, if you try to add everything, this one, it comes to 4.2 meters. 10.3 minus 10.3 minus your 5.8. If you do, I'm saving around 10.3 minus 5.8. I'm saving around 4.5 meters, 4.5 meters. This is your saving. Okay. So in the second case, that is your cylindrical. See, first case, if you look at it, this is only 2.5. But in the second case, I'm able to say that my cylindrical, that is, sorry, if it is a conical, if it is a conical draft tube, I am able to save 10.3 minus 5.8, that is 4.5 meters head of water is saved. That means that is the amount of energy I am able to save and I am able to convert it. So there is a better conversion because P2 is much less compared to your P2 in the cylindrical conditions. So this is how you people can solve the numericals, whether it's a Francis turbine or whatever.